This research is to be presented at CASA 2019. Part of the work has also been presented as a poster at IEEE VR 2019. 360 video is a popular and efficient way of capturing the real world for virtual reality. One of its major strengths is its ability to capture people in motion, talking and interacting naturally, with high visual fidelity. However, contrarily to 3D meshes, video assets cannot easily be made to react to users' actions in VR, nor provide a convincing sense of 3D depth and parallax. Consequently, many VR applications prefer to rely on 3D assets instead. In this paper, we seek to evaluate the extent to which learning-based models can help us get the best of both worlds by automatically generating 3D characters and scenes from 360 videos. We present a complete pipeline based on available pre-trained human mesh generation models and detail how we apply these models, trained on planar images, to our input spherical images. We also present the results of a user study, investigating the extent to which our generated virtual agents can be made more compelling by the use of idle animations and reactive verbal and gaze behavior. Many recent works have tackled the problem of estimating 3D human pose, shape, and texture parameters from images and videos, and have made their models and pre-trained weights available for research. However, most models are trained on datasets containing planar images, which causes many of them to fail on our input spherical images. One solution would be to retrain the models on spherical image datasets, but this would require having such a dataset and would be quite time-consuming. Instead, we propose to reproject our 360 images onto a virtual pinhole camera, given the right parameters so that it faces entirely, and almost only, the person of interest. In a first step, we use AlphaPose, a multi-person 2D human pose estimation model, to generate bounding boxes for the people in our scene, since we found this model to be one of the few to work quite consistently on our input images. We then create a virtual pinhole camera and focus it on one of the bounding boxes. Doing so for every frame therefore gives us a planar video, focused on the person of interest. Using the obtained planar videos as input, we can then directly apply our selected models for human pose, shape, and texture estimation. Namely, we estimate shape and pose parameters for the simple character mesh, using the pre-trained weights of the human mesh recovery model, and then use these parameters to create a 3D character mesh with animations in the Unity game engine. Note that since we have our character's estimated 3D pose in the virtual camera's local space, as well as the virtual camera's parameters, we can directly reposition our character in global 3D space. All that remains is to estimate the character's texture map, which we do by applying the pre-trained dense pose model. We also estimate a 3D scene from the video's background, which we do by applying the pre-trained OmniDepth UResNet model for 360 depth map estimation. What we now have is a dynamic 3D scene, complete with animated characters. In a second step, we seek to evaluate the extent to which these animated character meshes are perceived by users as being convincingly responsive. We therefore led a user study to investigate whether agents given idle animations and reactive behavior will more often be interacted with and given more personal space. We also studied whether showing participants a segment of the original video beforehand makes the agent feel more engaging. 50 volunteers took part in the study. The results validate the hypothesis that giving the virtual agent interactive features contributes to increasing users' feeling that it is a responsive entity, and encourages users to get closer to interact with it while still remaining outside of its personal space. However, the results do not validate the hypothesis that there would be benefits to previewing a segment of the video before seeing the character mesh. Users' main point of concern after the experience was the quality of the texture map, especially since it blurs out important facial features. Conversely, the quality of the estimated animations was found to be a strong point. In conclusion, we presented in this paper an investigation into the use of learning-based methods for the automatic generation of virtual agents from 360 video for interactive virtual reality. This work included an evaluation of users' perception of the generated characters' responsiveness, when these characters were given idle motion, as well as reactive verbal and gaze behavior.